Hello guys, Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera. So today I'm going to talk about supercapacitor. So total we have around 12 of 13 episodes. So the first episode is about cyclic voltammetry 3-electrode system. So this is a brief knowledge about supercapacitor. So at the first episode, I would like to talk about the cyclic voltammetry in 3-electrode system. So for your information, it will be a series video. So you can see a lot of episodes in one folder is about supercapacitor. So if you're new to supercapacitor, you can actually do the experiment if you follow the guideline one by one. So the first episode is about cyclic voltammetry 3-electrode system. So have you heard about cyclic voltammetry? So if you have the potential stat, so actually you can run the cyclic voltammetry because cyclic voltammetry is an analysis where you fix the potential. Then you can get the response in terms of current. So you divide by mass or you divide by volume, you get the response on the current density. So that's the main purpose of this analysis. So in supercapacitor, 3-electrode system is an important analysis that you should run first because you want to know the properties of your material. Because cyclic voltammetry, the main purpose is to study the behavior of your material and the electrolyte. So first thing comes first, which electrode should we use? So normally for cyclic voltammetry, you should use 3-electrode system, whereby you should have your working electrode, means that your substrate with your electrode, then you have your reference. Normally people use saturated calcium electrode or AgCl. Then the third one is the counter electrode, which is the platinum wire or whatever kind of platinum. You can have a coil platinum wire or a straight line platinum wire. Never mind. But the coil one is better because higher surface area. Okay, let's go things make it more easier about cyclic voltammetry. So if you have a new material, you want to venture a new material, we take a very small example. Okay, let's say I want to do a deposition by varying the deposition time. Means I want to produce my material, for example metal oxide. Then I want to differentiate the time. For example, I want to deposit for 5 minutes, 10 minutes, or 60 minutes, 1 hour. So I want to see what happened, what is the changes of the behavior of the electrode with the electrolyte in terms of the performance with specific capacity or specific capacitance. So let's say we have three materials, A, material B, and material C with different time. So what you need to do, fix one scan rate. Normally, you are using 5 millivolt per second or 10 millivolt per second. Bear in mind, the higher the scan rate, the lower the specific capacitance. Normally, we fix to 5 millivolt per second. So you can go to 1 millivolt, but the cycle will be very slow and it will consume time. So just go to 5 millivolt per second. And that's step number one. Step number two, understanding the behavior of your material, whether the potential window should be in positive region or negative region. So, for example, most of carbon-based material, the potential window at negative region. So you need to scan from 0 to -1 or -2 to see the limit of potential window of your material. If your material, for example, metal oxide, for example, we have nickel oxide, cobalt oxide, manganese oxide, most of the potential window at the positive region. So you need to scan from 0 to 1 or even 0 to 2 volt to see your potential window. Let me share you a lot of metal oxide bimetallic oxide, their potential window around 0 to 0.5, some is 0 to 0.6, or some can be 0 to 0.8. So depend on your sample and substrate and also electrolyte. So let's say our potential window is from 0 to 0.5. So now we already know about the potential window. So we already fixed the scan rate to 5. Why we fix this? We're going to run the CV for 3-electrode system for our 3 material earlier, material A, material B, and also material C at 5 millivolt per second from potential 0 to 0.5. Then we observe the cyclic voltammogram. What we're going to observe, number one, is the shape of your CV. So, talking about the shape of your CV, we have a basic shape. Shape number one is EDLC-based material, which is carbon-based material. The shape, if ideal supercapacitor, is rectangular shape. It's like a rectangular shape. But normally we don't get perfect rectangular. But if you get almost rectangular, means your material behavior is EDLC. Second shape is leaf shape of, or we call that distorted rectangular. You can say about quasi-rectangular. Okay, this is the behavior, like a leaf shape behavior for the pseudo-capacitor-based material. If you have something like shape of leaf, so this is a pseudo-capacitor behavior. If you have a very distinctive redox, anodic peak and cathodic peak, very distinct, means that very apparent, very, what we call that, very obvious redox peaks. So this is a battery type shape. So normally we have 3 shapes. So remember for the CV. So determine which material. For metal oxide, normally you should have either leaf shape or you should have the battery type, depend on the material. If nickel oxide, you can see obvious redox peaks. But for copper oxide, normally not very obvious, but still have the redox peak. So depend on your material. So number one, we want to observe the shape. Number two, you're going to observe the response, specific current. You're going to see the current density. So we have 3 samples A, B, C. So when you run one CV at 3 samples at 1 scan rate, you can see the difference in the current density. So the highest the current density is the better, because it produces high specific capacitance. So based on this 3 samples, you can see which deposition time is the best for your material. Okay, so normally people say, how many cycles we going to run? 1 cycle, 2 cycle, 3 cycle. Minimum is 2 cycles. Normally we pick the cycle number 2 because the first cycle normally a little bit higher due to wetting and activation process. However, depend on your substrate. If you are using nickel form, you need to activate, for example, for 5 minutes or 10 minutes, because the activation or wetting process taking much longer time compared to the other substrate. Okay, so I said minimum is 2, but you choose 3 cycles for your screening CV. This CV, cyclic voltammetry 3-electrode system, we call that screening CV, to determine roughly which sample is the best. Okay, after we do the experiment, we know that, for example, sample B get the higher current response. So we know that B have higher current response and higher surface area per unit volume. So we're going to prove that. How to do that? Take your data, your x-axis is the potential, y-axis is your current, and put in the origin and calculate. Click the analysis, integrate, and you get the area under the curve. So basically, the higher the current response, the area is also bigger. So bigger area will also lead to higher specific capacitance, but also depend on your mass also. Supposedly the mass not vary too much if you are using technique like electrodeposition. Okay, enough with that. That is a cyclic voltammetry 3-electrode system. So should we stop here? No, we should not stop here. You should continue your experiment. Don't be too excited. It's just one small part about 3-electrode system. Then what you need to do next is cyclic voltammetry at different scan rate. So at different scan rate, you have 2 choices. Either to run all 3 samples at different scan rate, or you can choose the best sample to run at different scan rate. Depends on your availability, your time, your resources, and your skill. and what do you want to put in your paper. So it's totally depend on you. So what normally I do, I just pick the best sample and go for cyclic voltammetry at different current, different scan rate. However, you can do for all sample because I already do the optimization using response surface methodology. So it is not necessary for me to do for all the sample. So I pick the optimized one, the highest current density, not the highest, the best sample with higher current response. So I run cyclic voltammetry 3-electrode system at different scan rate. So how to vary the scan rate? You can vary from 1, 3, 5, 10, 25, 50, 75, 100 millivolt per second. All depend on your material. What I notice is for battery type material, the battery behavior doesn't maintain at high scan rate because battery material, the process of redox normally occur at slow scan rate. That's why normally I do less than 50 millivolt per second. Sometimes even goes up to only 30 millivolt per second, depend on your material. Because from this analysis, you want to observe the change in the shape of your graph. If your shape of graph different greatly, so it will affect the reversibility of your material. So you need to, what we call that, you need to be genius in terms of understanding the limits of your material and how high the scan rate can be. If, for example, at low scan rate, it shows obvious redox peaks. But when you increase up to 50, 100, 200 millivolt per second, you didn't even see the redox or the battery type or the redox peaks anymore. So it is not necessary to run until that higher scan rate. So it depends on you. So mainly for this analysis, we want to see either the shape of your CV retain or not. Okay, then you can actually plot the specific capacity versus the scan rate to see the trend in your specific capacity. So the trend normally reduce when you increasing the scan rate because not enough time for the electrolyte ion to penetrate the bulks of your electron. Because at lower scan rate, the electrolyte ion move very slowly. They have enough time to go and pass through and penetrate the surface of your material and the bulk of your material. And if you increase the scan rate, the electrolyte ion can only contact with the surface of your material. That's why you can see that redox process occur at the bulk of your material. That's why the shape of redox, when you increase the scan rate to higher scan rate, you might not even can see the obvious redox peaks. Okay, I think I covered all about the cyclic voltammetry for 3-electrode system. I think that's all. See you in the episode 2. Okay, bye. See you again.